Good day, everyone, my wonderful viewers. How we're doing today? I believe you're all great. Welcome to the channel once again. We're going to be looking at a very interesting topic in chemistry that you're going to learn a lot from. And this video is going to be a bit lengthy, so ensure you're watching this video during your leisure hour. So get your notebook, get your pen, and let's learn. So the topic before us today is organic chemistry, and we have a lot of things to discuss. So we're going to start with the definition of organic chemistry. We need to know the meaning of organic chemistry. So organic chemistry is simply a branch of chemistry that deals with the study of matter, not just matter now. We're talking about carbon as matter. Remember, the universe is made up of matter, and matter is made up of basically elements. And in chemistry, we have over 100 elements. But one of these elements stand out, which is carbon. So scientists decided to give carbon a branch on its own. So organic chemistry is a branch of chemistry that studies carbon compounds, excluding the oxides of carbon and the triazocarbonates. So the oxides of carbon, we have carbon 4 oxide. Okay, so we have carbon 4 oxide. We have carbon 4 oxide is CO2. We have carbon 2 oxide, and then we have the triazocarbonates. The triazocarbonates are compounds that contain the triazocarbonate 4 radical group. For example, calcium triazocarbonate 4. So the study of organic chemistry, the scope of organic chemistry doesn't extend to the oxide and the triazocarbonate. But every other compound of carbon can be classified as organic compounds. So we've learned the definition of organic chemistry, a branch of chemistry that deals with the study of carbon compounds, excluding the oxides and the triazocarbonates. Now, the next question that we should be asking ourselves is, what is so unique about carbon? Why did scientists decide to give carbon a branch on its own? There have to be something unique about carbon. So let's discuss the uniqueness of carbon. Carbon is an element that forms numerous compounds, a lot of compounds, millions of compounds. And its ability to form millions of compounds is attributed to some unique characteristics it possesses. One of such unique characteristics is the ability of carbon to catenate. So we have the ability of carbon to catenate. So what do we mean by the word catenate or catenation? It simply refers to the ability of carbon to form long continuous chains. So as we're going to see in the course of this topic, carbon can form a long chain of covalent bonds between itself. Hence, the term used to describe that ability is what we call what? Catenation. So that's the first attribute of carbon that makes carbon unique. The next attribute of carbon that makes carbon very unique is the fact that carbon is tetravalent. So we have tetravalency. Yes. So carbon is tetravalent in the excited state. What do we mean by saying carbon is tetravalent? It means that what? Carbon have the ability to form 4 covalent bonds with itself and then atoms of other elements such as hydrogen, oxygen, nitrogen, the halogens, especially these. Okay, so the ability of carbon to form bonds with this element is due to its tetravalency. So carbon is able to form what? 4 covalent bonds. Hence, we say carbon is tetravalent. That's another reason. The fact that it can form 4 covalent bonds makes it possible for you to form a lot of compounds, because those positions, those covalent bonds can be formed with different elements such as this. Also, another property that makes carbon very unique as an element is its ability to form multiple bonds. Yes. Since it is tetravalent, carbon can actually form multiple bonds with either itself, atoms of other carbon, or atoms of other elements such as oxygen and what? Nitrogen. So that is another reason why carbon is unique. Its ability to form multiple bonds such as double bond and triple bond with itself and then other elements. All these contribute to the reason why carbon forms a lot of compounds. Having discussed the uniqueness of carbon, we're going to talk about the hybridization of carbon, which is one aspect that you would be tested on in your exam. So, talking about hybridization of carbon, what is the meaning of hybridization? Hybridization is simply the mixing of atomic orbitals. The mixing of atomic orbitals of equivalent energy to form more stable orbitals that can be used for covalent bonding. For this concept to make much sense, I'm going to take up what I have on the board, okay, and then we discuss hybridization, in details, all right? Okay, now let's look at hybridization as a concept in chemistry. I've just told you the meaning of hybridization, where I said hybridization is the mixing of atomic orbitals. So I think it is paramount for us to know the meaning of what an orbital is in chemistry. An orbital is simply a region. Remember, in chemistry, an atom is made up of a nucleus, and then we have electrons around this nucleus. Yes. So, a region around the nucleus of this atom, this is the nucleus, where there is a high probability of finding an electron, is what we call an orbital. So, orbitals in chemistry are found in what we call sub-energy levels. So orbitals are found in sub-energy levels, okay? And sub-energy levels are found in energy levels. All right? So it's just like, I'll give an analogy of a building. So if you have a building, if you are looking for your friend, your first point of thoughts will be the building where the person is staying. When you get to that building, the next thing is to locate the room, because in a building you would have different rooms. You agree with me? So if you have a building, your friend will be found in a particular room in that building. Get into the room where your friend is found. If the room, of course, most rooms have different bunks, bed spaces rather. So your friend has a particular bed in that room. So if I ask you, the region in that building where there is a high probability of finding your friend now becomes the bed. Just an analogy. Same way in chemistry. So the building in this analogy is likened to your energy levels. Your energy levels. Okay? The rooms in that analogy is likened to your sub-energy levels. And then the bed in that analogy is now likened to what we call your orbital. All right? Now, talking about sub-energy levels, we have 4 sub-energy levels in chemistry. The sub-energy levels we have the S sub-energy level, we have the P sub-energy level, we have the D sub-energy level, and then we have the F sub-energy level. So remember, sub-energy level is likened to your room. So every room have a number of beds. So every subenergy level have a number of what? Orbitals. So an orbital can be found in the S subenergy level. It can be found in the P subenergy level. It can be found in the D. It can be found in the F. So when we're talking about hybridization as a concept, it is the mixing of different atomic orbitals. So atomic orbitals now can be S orbital, P orbital, D orbital, and F orbital. For the scope of this lecture, we'll be limiting ourselves to just the S and the P orbital, as those are relevant in the subject of hybridization in context of carbon. All right. Now, you should know that an S orbital is spherical in shape. So S orbital, they are what? They are spherical in shape. Spherical, this is how we draw our S orbital, just a circle. While the P orbital, they are dumbbell in shape. Dumbbell in shape. This is how they look like. Either like this or this way or in this direction. So these are the shapes for your S and your P orbitals. So the question is, why do we need to mix up atomic orbitals? When you say hybridization is the mixing of atomic orbitals, why is it necessary to mix up atomic orbital? Hence, this rule is written here for us to see. I said here in covalent bond formation, different atoms of one element, say A, uses same orbital type to overlap, to bond with a set of identical orbitals of another element, say B. Now, for this to make sense now, we're going to look at carbon as an element. Quickly, then we'll take this off the board. All right. So, talking about carbon as an element, we have carbon in the ground state. Let me write it. Carbon, ground state. Now, the ground state's electronic configuration of carbon, in case we don't know, carbon is atomic number 6. So we all know that the configuration of carbon is 1s2, 2s2, and then 2p2. This is the electronic configuration of carbon. So if I'm to draw this in the box diagram notation, it's going to be in this format. We have our first bus. We have our second bus. So this is the bus for our 1s. We have our second box. And then this is for 2s. And then we have the 2p. A p orbital has 3 buses, 3 possible orientation, just like I drew. Okay, so we have our 2p. So in the ground state configuration of carbon, we can see that the 1s orbital takes 2 electrons. So an electron spin upward and the other spin downward, according to Pauli's exclusion principle. So we are filling in for 6 electrons. This is 4 already. This is 5, and then this is 6. So this is carbon in the ground state. Ground state means in the normal state of what? Of carbon. Now, in the excited state of carbon, one of the electrons in this 2s orbital would be promoted to this vacant orbital during excitation. An electron becomes excited when it absorbs what? Energy. So when this atom absorbs energy, one electron here would be promoted this way. But I expect you to be asking me a question here. Now, what's the question? The question is, why weren't we promoting an electron from this? Now, the reason is this. During excitation, it's very much more easy for electrons in equivalent energy, electrons with equivalent energy to be promoted. So the energy level for this orbital here is 2, but the energy level for this orbital is just 1. So you are permitted to promote an electron from one orbital to another orbital of equivalent energy. This is 2, and then this is 2. So if I should promote this to this empty box here, we now have our carbon in the excited state. So I will say carbon's excited state. So we draw. This is your first bus, 1s. You draw your second bus. There's 2s. And then you draw your third bus for your 2p. All right. So let's fill our electrons. These 2 electrons still remain intact. We're not promoting those because the energy level is 1. Then this bus now has just 1 electron. This has 1, 2, and then 3. Now, just in case you're asking, why didn't we pair this electron with this? Why didn't we do it this way? According to Hund's rule, before we start pairing electrons in degenerate orbitals like this, we must fill those degenerate orbitals singly first. Hence, we give the 1 this way. So that's why it's done that way. So this is carbon in the excited state. So in the ground state of carbon, we can see that what? The valency of carbon is 2. Valency simply means the number of electrons available for bonding. So we have just 2 electrons that are free and available to bond. But in the excited state, we can now see that what? Carbon is tetravalent, in the sense that it now has what? 4 electrons available for bonding. And remember, we have established that one of the reasons why carbon is very what? Unique is because of its tetravalency. So the tetravalency of carbon is not explained, cannot be explained in the ground state of carbon. It's only explainable in the what? In the excited state of carbon. But the problem now is, can we now bond carbon with other atoms using this excited state configuration? The answer is no. Why are we saying so? Now, hydrogen, let's use hydrogen as an example. The atomic number of hydrogen is 1. So the electronic configuration of hydrogen is 1s1. So if I am to draw hydrogen, hydrogen would look this way. A box, that box would be 1x and it will contain just 1 electron. So for hydrogen to become stable, it needs a second electron to occupy this particular orbital. So if I have 4 hydrogens, we can clearly see that each of those hydrogen, just like what we learned in our preliminary classes, where we draw carbon as atomic number 6, 1, 2, 3, 4, 5, 6. Okay? Then each hydrogen, if I have 4 hydrogens, they come with their single electron. This single electron here, they bring them over and then they overlap. What I'm doing here now is what we call overlap or bonding. So these are covalent bonds being formed. These are hydrogens. These are hydrogens, all hydrogens. So this is what happens. So 4 of these hydrogens overlap with each of these electrons you are seeing of the carbon. These are the electrons of the carbon, as you can see, the star. And then these are the electrons of the hydrogen, the dot. So this is a diagram in the energy level sense. But if we are not explaining in terms of energy level, I should be explaining in terms of orbitals. So we're looking at orbital explanation. So in the orbital diagram, we can see we have 4 electrons available for bonding in carbon, just like we can see in the shell configuration. So each orbital of hydrogen would bond 4 hydrogens now. Each of them will bond with each of these orbitals. But is this really obtainable? Can this hydrogen just come and overlap with this, and this? It's not possible. Now, why is it not possible? Because of this rule. Let's read the rule again. In covalent bond formation, different atoms of one element. So the different atoms of one element we're talking about now is the different atoms of hydrogen. Okay? Say A uses same orbital type. What is the orbital type of hydrogen? The s orbital. To do what? To overlap, meaning to bond with a set of identical orbitals of another element, say B. The other element is carbon now. So it means that what? Hydrogen, the orbital of hydrogen, which is this s orbital, can only bond with identical orbitals of carbon. So the orbitals where these free electrons are different. This electron is found in the s orbital, while these electrons are found in the p orbitals. So it is not possible, according to this rule, for the orbital of hydrogen to go and bond with different types of orbitals of carbon. So this contradicts the rule. Hence, the concept of hybridization. Now, what can we do now to ensure that the orbital of hydrogen bonds with identical orbitals of carbon? What do you think we can do? It's just like you have a number of kids. This number of kids all want ice cream, and you have different flavor of ice cream. Let's say you have vanilla flavor, and then you have, let's say, banana flavor, whatever you call it. Now, you have 4 kids, and these 4 kids are saying that they all want the same ice cream. So what are you going to do? And at the same time, these kids are saying they want to have a taste of all the flavor of the ice cream. What would you do as a parent? Simple. You simply mix up both ice creams together, isn't it? So when you mix up both ice cream and you distribute to the 4 kids, everybody gets satisfied because they all taste identical taste. You've mixed them up. That is using ice cream, using that ideology now. Each of the atoms of hydrogen wants to bond with the same type of orbital in carbon. How is this possible now? Since this is an s orbital and this is a p orbital, the only thing we can do now, just like you mixed up the ice cream, you are going to mix up your p orbital and your s orbital. So when you mix up this orbital, the process of you mixing up atomic orbitals of equivalent energy, this is 2 and this is 2. That process is what we call what? Hybridization. All right, so I will take this off the board so I can draw the hybridized state of what? Of carbon. Okay, now let's draw the hybridized carbons, hybridized state. All right. Now, we have carbon undergoes 3 types of hybridization mainly. We have the sp3 hybridization, we have the sp2 hybridization, and then we have the sp hybridization. So what is the meaning of sp3, sp2, and sp1? It simply refers to, remember, carbon have 4 orbitals that are available for mixing now. Just, okay, so we have these 1, 2, 3, 4, so we want to mix them. So we have 1 s orbital and 3 p orbitals. If you successfully mix up all 4 orbitals, the type of hybridization that you're going to have for carbon is now what we call sp3 hybridization. Meaning we are missing 1 s orbital with what? 3 p orbitals. So let's see how this diagram would look like. It's going to look like this. You have your first. This is 1. Then this and this, you've mixed them up. So you have 4 orbitals whose energy level will lie between the energy levels of this and this, somewhere between them. So I'm not putting this box at this level. I am not putting it at this level. It's somewhere a bit higher than this and a bit lower than this when you're drawing. So I'm going to draw 4 buses. All right. So this is your 1s orbital, but this now is your sp3 orbitals, sp3 hybrid orbitals. So this retains its 2 electron here, and these 4 orbitals retain their 1 electron each. 1, 2, 3, 4. So we call these orbitals here now, we call them hybrid, let's say sp3 hybrid orbitals. They are hybrid orbitals because we mixed them up. So you can now see that each of the atoms of hydrogen can now successfully come and bond with each of these orbitals. Why? Because each of these orbitals, they are now identical. If I ask what's the name of this orbital, you will not tell me it's an s orbital again. No, it's now called an sp3 orbital. It's just like when you mix up 2 flavors of ice cream, strawberry and vanilla. If I ask you what is the name of this mixture of ice cream, you cannot say strawberry, neither can you say it's vanilla. It is a mixture of both. So each of these buses now, they lose their individual names and we call them sp3 hybrid orbitals. So the orbitals of hydrogen would now be bonding with what? Identical orbitals of carbon, obeying our basic what? Our basic rule. So this is simply what happens with what? Hybridization. But what I just explained now is what? For sp3 what? Hybridization. I'm going to draw the geometry. From this hybridization, we can be able to predict the geometry of a molecule. So we're going to learn how to do that shortly. But before we do that, remember, for emphasis sake, that the shape of an s orbital is spherical. The shape of a p orbital is double dumbbell. Sorry, dumbbell. So it can be in this form. It can be in this form. It can be in this form. Now, when you mix an s orbital with a p orbital, just like mixing 2 different flavors of ice cream, the shape, which is the shape for an sp orbital, hybrid orbital, looks this way. Yes, still the double dumbbell, but one of the lobes become extremely tiny and small. And hence, for the course of this topic in my tutorial, I might just draw it this way. So this is the shape for these orbitals that you are seeing. This is how I would be drawing it in this topic. So how do we now draw the geometry of what now? Of carbon in the sp3 hybridized state. I'll take this off the board and then I show you how you do that briefly. Okay, now let's learn about the geometry of each of these hybridization. Now I wrote something very important here. I said, the hybridization theory assumes that atomic orbitals mix to form hybrid orbitals, which are oriented in space to minimize electron-electron repulsion. Remember that in each of these orbitals, what exists in them, what lives in them, are what? Electrons. And electrons are negatively charged. So since each of these orbitals, remember I've told you that I'll be drawing the orbitals like this. So if each of these orbitals are having 1 electrons in them, you should infer that what? They will tend to repel each other. So they repel themselves to a maximum extent where they would be stable. So we have what we now call the stable configuration or geometry of each of this hybridization. So I'm going to be drawing carbon in the sp3 hybridized form. So this is carbon. Okay, this is carbon. And then we have our first hybrid orbital in this direction. This is the first hybrid orbital. You have another hybrid orbital this way. You have another, the third hybrid orbital. Then we have So this is what we have for each of your hybrid orbital. All right. So remember, each of these hybrid orbital 1, 2, 3, 4 accommodates one electron each. So I'm gonna use a different color of marker to indicate that. All right. So we have one electron. We have one electron here. We have one electron, and then we have one electron here. So this is the geometry of the sp3 hybridization. Now, if I'm to use the line notation, it's going to look like this. This is how the hybrid orbitals orient themselves in space. So this is how they orient themselves in space. Now, this full line you're seeing is trying to tell us that what? Three of these lobes actually lie on the plane of the board, while this dash bond shows that what? This particular hybrid orbital projects out of the board. Okay, so that is the interpretation. So it's just like the structure of a tripod. Okay, you know, in a tripod, you have the parts that is standing straight, then you have three legs. One of the leg most likely points to the back. So this is what you have. So that is the configuration for your sp3. That's the geometry of your sp3 what? Hybridization. So the angle between each of these bond is 109 degrees. The angle between each of those hybrid orbitals. Remember we said the hybrid orbitals will repel themselves to a maximum extent. They will push each other far apart. So this is exerting a repulsive effect on this. This is also exerting a repulsive effect on this. Each of them exert that repulsive effect on themselves. Hence, the geometry at which the configuration becomes stable is when the bond angle, not the bond angle now, when the angle between each of these hybrid orbitals is 109 degrees. That's where you have your stable geometry. And the name of this geometry is called the tetrahedral geometry. So this is what you obtain for your what? For your sp3 hybridization. So when hydrogen, remember the configuration of hydrogen, which has atomic number 1 is 1s1. So, and an s orbital, remember we said an s orbital is what? Is spherical in shape. So if I have 4 hydrogens, each of those 4 hydrogens overlap in this manner. So that's the first hydrogen overlapping there. There's the second hydrogen. This is the third hydrogen. This is the fourth hydrogen. And remember, each of those hydrogen have 1 electron in those orbitals. So the region where they overlap, which is this region, the region where this circle overlap, this hybrid orbital will be this region here. So when you are placing the electron for hydrogen, you place it within the region of intersection. So you don't go and place the hydrogen in this region. No. This region isn't overlapping into your what? Now your hybrid orbital. So you must place the hydrogen electron inside. So remember, they will have opposite spins. This points down, and then this points down. And remember, these are hydrogen orbitals. So this is the structure of a compound, which is CH4, 1 carbon and 4 hydrogen. So the hybridization, the name of this compound, as we'll learn later, is known as methane. So the hybridization in methane, if you are asked in your exam, the hybridization of carbon in methane is sp3 hybridization. I believe this is clear. So sp3 hybridization is always exhibited by a carbon atom that is bonded to four single covalent bonds. So if you have carbon, whenever you see carbon bonded to 1, 2, 3, 4, these are all single bonds, and then there are 4 in total. Whenever they ask you the hybridization of such carbon, you just say the hybridization is what? sp3. If I should write this and then I put a double bond this way, like this, and then I ask you, what is the hybridization of this particular carbon? You cannot say it's sp3. Why? For this carbon, this is a single bond, this is a single bond, but this is a double bond in here. So the hybridization of this carbon is not sp3. So this brings us to the end of sp3 what? Hybridization. We go over to the what? The second type of hybridization, which is what now? Our sp2 hybridization. I'll be taking off what I have on the board and then we dive right at it. All right. Now let's talk about sp2 hybridization quickly without wasting time. Now, when you hear the word sp2 hybridization, what does it mean in carbon? sp2 hybridization is simply, so I'll say note, sp2 hybridization is simply the mixing of one s orbital with 2 p orbitals in carbon. So this is what we're going to be mixing under sp2 hybridization. So we'll repeat the same diagrams for understanding's sake. Remember, we have carbon ground state, carbon ground state. From the ground state, so this is carbon ground state. Then we go to carbon excited state. And then we have carbon in the hybridized state. So in the ground state of carbon, we know what's obtainable. We have our 1s, our 2s, and then we have our 2p. 1s, 2s orbital, and 2p. So we have 1, 2, 3, 4, 5, 6. So this is carbon in the ground state. Now let's look at carbon in the excited state. We have 1s, we have 2s, and then we have 2p. So this is 1, 2, 3. So we promote 1 electron to this empty orbital. 4, 5, and then 6. So then in the hybridized state, remember what are we doing in this hybridization? We are only mixing this orbital with 2 of these orbitals. So we're going to have our 1s as usual, which nothing happens to essentially. So we have 1, 2, and then we have our hybrid orbitals. In this case, we have just how many orbitals here are we missing? There are 3. 1, 2, 3. So this is 1, 2, and 3. So this is sp2 hybrid orbital. Then we have 1 orbital would be left that wasn't missed. So this orbital will be at a higher energy level. All right. So let's fill in our electrons. So we have 1, 2, 3, 4, 5. So this is 1, 2, 3. We'll fill that. So this orbital still retains its 1 electron. So this is what happens during sp2 hybridization. So let's draw the geometry of carbon in the sp2 hybridization quickly. Okay. So in the sp2 hybridization, this is how we draw the structure. So we simply say carbon is at the center of it all. And then how many hybrid orbitals? So we have 3 hybrid orbitals. Okay, so let's draw our hybrid orbitals. We know how to draw our hybrid orbitals. So we have 1, Then we have 2, 1, 2. Let's tilt this a little. Sorry. Okay. So we have 1. Okay. Then we have 2. And then we have 3. Okay. Then remember we have one orbital that was not hybridized. So we're going to draw this way. Since it's a p orbital, remember p orbitals have 2 lobes. So these are the 2 lobes for the unhybridized orbital. So I would shade my hybrid orbitals to differentiate them from the unhybridized orbital. So these represent your unhybridized p orbital. While these shaded ones represent your what now? Your hybrid orbital. So this is what you have for the geometry of your sp2. So the sp2 configuration is actually a planar structure. So the planar structure, the bond angle between each of these hybrid orbitals is actually 120 degrees. So we have, so essentially this is what we have in that structure. So the angle between this and this is 120 what? Degrees. Take note of that. The bond angle under sp3 for sp3 hybridization is 109, approximately 109. But for sp2, our bond angle is 120. That is the angle from the center of this lobe now to the center of this lobe. So the angle here is 120. So that's the 120 we're talking about. So that gives you, and the name of this is what now? We call this our what? Our trigonal what? Planar structure. Take note of that. We call this our trigonal planar geometry. So the geometry or the shape of the sp2 hybrid orbitals, hybridization in carbon is what? Trigonal planar. Take note of that. Now, an example of a compound that have carbon atoms that are sp2 hybridized is what? Ethine. Sorry, not ethine, ethene rather. So we're going to draw ethene and we're going to study what actually happens in the bonded sequence of what? Of ethene. I'm going to take this off the board quickly, shortly. All right, now let's look at ethine. We're going to learn later how to get these formulas, but for now, the formula of ethine, not ethine, sorry, we're going to be using ethene to explain sp2 hybridization. Ethene is C2H4, so we need 2 carbon atoms. Remember, this is how the structure of sp2 hybridization is for 1 carbon. So we're going to bring another carbon of this. Just imagine this, another one over here, and then we're merging them up together. What are we going to have? We're going to have a structure that will look like this. So we have carbon at the center. We have our unhybridized orbital, the p orbital that wasn't hybridized. Okay, then we have these 2 hybrid orbitals this way. So I will shade them to differentiate. All right, then we have this last loop. Now, if you bring another carbon atom and then you merge them up, okay, you flip this carbon the other way around and then you merge them up, you are going to have something that would look like this. Okay, then we have another carbon over here. The same sequence repeats itself. There's the unhybridized, there's unhybridized, Okay. Okay. Now this region here constitutes, remember this carbon here would have this lobe that is pointing straight. This other carbon also have that lobe. So these two lobes have merged up. Hence, this region is looking bigger because this is the measuring up of this. So this is the measuring up of this for one of the carbon and this for the other carbon to give you this. Okay, so we have our electrons. Let's place our electrons in therein. Remember in our diagram, each of these have one electron. So this is one. This has one electron. This also have one electron. Even the unhybridized orbital still has one electron. Refer back to the diagram we drew. So we have one electron here. We have one electron here. Then for this carbon, we have one electron. For this other carbon, due to the merging we did, there is another electron. So we have two electrons in this region. Since we merged up two of this to form this big region. Take note of that. So we have our one electron here. We also have our one electron for this other carbon. Remember, these two lobes represent your p orbital, the unhybridized p orbital. Now, for us, so we have gotten our two carbon, so we have four hydrogens here that wants to be stable. So what would happen? One of the hydrogen would overlap in this region with its one electron. Another hydrogen overlaps in this region with its one electron. Another hydrogen, remember this lobe, there is a bond here, this and this, an electron. We have another electron. So an hydrogen atom can come here with its electron and overlap. Another hydrogen can come here with its own electron and then overlap. So we have, this is hydrogen, this is hydrogen, this is hydrogen, and then this is hydrogen. But then we still have something left. What's actually left now? This electron is still here without a pair. And for this compound to be possible, all electrons must be bonded. So what would happen? This electron in this unhybridized orbital would bond with this electron in this unhybridized orbital. So I'm going to use a broken line to show that bonding. So there's a bonding sequence that is occurring between these two unhybridized orbitals. So when they overlap, whenever atomic orbitals overlap side by side, we have what we now call what? We have pi bond formation. I repeat, we have two types of bonds with respect to this topic that you should be familiar with. We have pi bonds and then we have sigma bonds. Now, pi bonds are formed from the lateral overlap. Lateral overlap simply means side by side overlap. So we have this and this, what? Overlapping. Okay, so we have, if we have one orbital and one orbital overlapping side by side, we also call it parallel overlap. Just like this, one and one, so they are overlapping with each other with this broken line. So that's parallel overlap. That parallel overlap constitutes what we call what now? The formation of a pi bond. So this bond over here is a pi bond. So this is a pi bond. These are our electrons. Let's make them visible. So we have electrons in this region, remember. So this is a pi bond. Now, when are sigma bonds formed? Sigma bonds are actually formed when we have head-to-head overlap of atomic what? Orbitals. Head-to-head overlap of atomic what? Orbitals, as we can see. So let's use this marker for illustration. If we have, this is an atomic orbital, and this is a second atomic orbital, and then they are overlapping head-to-head. So the head-to-head overlap of atomic orbitals leads to the formation of sigma bond. So if this marker should overlap head-to-head, we call this a sigma bond. So you can see hydrogen is overlapping head-to-head with each of these. So in here we have sigma bonds. So the symbol for pi bond is this, sigma. The symbol for this is this. So we have sigma bond. This is also a sigma bond. This is also a sigma bond. And this is also a sigma bond. But this is a pi bond. Why? Because we have a side-by-side overlap of your atomic orbitals. Now, take note, sigma bonds are usually what? Stronger. Take note of that. Sigma bonds are stronger but shorter than pi bonds. In case you are asked, take note of that. So when atomic orbitals overlap head to head, the bond between them tends to be very strong. So you should take note, another point you should take note of is that sigma bond exists in every single bond, present in single bonds. Whenever you have a single bond in a structure, for example, if I should draw this structure, okay, so in this structure, each of these your double bond, these double bonds here, they are all sigma bonds. So that's one key point that should be very much in our consciousness. All right. So talking about the strength of sigma bonds. Sigma bonds are stronger because they are short in length. The length of a sigma bond is very short, so they tend to be strong. Okay, you agree with me that it takes greater strength for you to break a wood that is very short. If a wood is very this short, it becomes difficult for you to break. So the bond holding the orbitals are stronger when the bond length is actually what? Short. So for pi bonds are weak bonds. Pi bonds are not strong bonds. Take note of that. All these will come into play when we go into organic chemistry proper. Take note of that. So I've just explained that what? Whenever you see a sigma bond, you should know, whenever you say a single bond, you should know that that bond is a sigma bond. This is a single bond, single bond. So every single bond you see, so is all these single bonds, they are all sigma bonds. But whenever you see a double bond, take note, whenever you see a double bond, one of them here is a pi bond, which is this pi bond you are seeing, while the other one here is a sigma bond. Now, this bond in this region is actually a sigma bond. Why is it a sigma bond? Remember that we measured up this lobe of one of the carbon with this same lobe of another carbon. We mesh them head on like this. That is why the drawing is in this format. So that head on overlap that we did between these two lobes constitute a sigma bond. It means anytime you see a double bond in organic chemistry, one of those double bond is a pi bond, while the other double bond there, while the other single bond is a sigma bond. So one bond is pi, the other bond is sigma, as we can see in this structure. So this illustrates sp2 hybridization. So we just talked about sp2 hybridization using what? Ethene. So whenever you see a double bond, that's the key point you should pick from this. Whenever you see a double bond, you should know that the carbon atom there is what? sp2 hybridized. sp2 what? Hybridized. Whenever you see a double bond. Whenever you see a single bond, you should know. Whenever you see a carbon is carrying just single bond, you should know that carbon is exhibiting sp3 hybridization. Now we're going to go over, take off everything on the board, and we'll end with our sp hybridization of carbon. Okay, now let's look at the final part of this video, sp hybridization of carbon. So the word sp, the notation sp means we're going to be missing just an s orbital and one p orbital. So without going through the ground state, starting from the excited state of carbon, which we already know as this, so we're going to be missing this with only one of these p orbitals. So in my hybridized form, these are the diagram would look like. So this is our 1s, which nothing happens to. So we have our hybrid orbitals. How many hybrid orbitals are we drawing? We have just two. So we have, this is our sp orbitals, and then we have two orbitals here that weren't used in the mixing. So these are the unhybridized orbital, which will appear at higher energy levels. Okay, so this is basically what we have. So 1, 2, 3, and then 4. So this represents your hybrid orbitals, and this represents your unhybridized orbitals. Okay, so let's draw the diagram, the geometry of the sp hybridization. So basically it's going to look like this: carbon at the center. So the geometry is a linear geometry. So we have our hybrid orbitals. Since we have just two of them, if these two hybrid orbitals should repel themselves to maximum extent, the geometry that they would assume will be a linear geometry of this nature. Yes. So these are our hybrid orbitals. I shaded them. So we have two unhybridized orbital for carbon. So how do we draw those? I'm going to draw them this way. So they aren't shaded. Now, why am I drawing a double lobe for them? Remember, these are what? These are p orbitals. These remain two p orbitals, okay? So, and p orbitals always have their double lobe. So this is the double lobe here, and then this is the double lobe here. So each of those contain an electron, like we can see. So we place the electron. So we have an electron here. We have an electron in this region. We have an electron here. We have an electron in this region. So we're not placing electrons here because this is for this electron is for this, and then this is for this. So this is what we have for the sp3 hybridization. It's a linear geometry, so if we should get the angle from this to this, that is 180 degrees. So take note, the geometry of the sp hybridization is a linear geometry. So this is a linear geometry with a bond angle of what? 180 degrees between the hybrid orbitals. Now, example of a compound that contains a carbon atom that exhibits the sp hybridization is what? Ethine. So I'm going to take this off the board and I'll show you how the bonding sequence occurs in ethine. Okay, I figured out, okay, we're going to need this diagram for the explanation. Let's leave this on the board. So let's draw the first carbon. In case we don't know, the formula for ethine in organic chemistry, which we'll learn in subsequent video, is C2H2. So in ethine, we have two carbon and then two hydrogens. So let's see how this bonding would occur. So let's draw for the first carbon. So for my first carbon, I have carbon at the center. Then we have this. Then we have our unhybridized orbitals. Okay. All right, before we draw that other lobe, remember that for this, if I'm having two carbon, one of these lobes here, we bond head to head with the second carbon over here. So I'm going to have something of this nature. So let's say this is our other carbon. Okay, so in this region, I've overlapped what? Two of these loops here have overlapped. One of this for one carbon and the other carbon is what is giving me this big loop here. So we have our two electrons there. So what type of bond would be present between those two loops if they are overlapping head to head? This will actually be a what? A sigma bond. Okay, then what we do next is, okay, I'll add the loop, the second loop for this unhybridized. Okay, so these are sigma bond. So let me shade for understanding sake. These are my hybrid orbitals. Okay, let me use a different color for the electrons. These are the electrons in this region. All right, so these are the unhybridized orbitals, which are these four. 1, 2, 3, 4. You place your electrons. So we have an electron here, an electron here. Then we have an electron in this region. All right, so we draw same for this other carbon. So I'm going to have this is for one, and then you draw for the other. Let me draw this in this direction. This isn't giving me what I want. Okay, so we have our one electron. We're going to have a second lobe. This lobe at the back, you position it for the hybrid orbital. So I'm going to shade this, and it has one electron also. So we place our one electron. So we have one electron for this, and then we have another electron for this. Okay, so we have another electron over here. So we have drawn for both carbons. Lastly, we are now going to place our hydrogen. How many hydrogens are we looking at here? We are looking at 2 hydrogens. So this is how they arrange themselves. So hydrogen will overlap head to head, which is a sigma bond, with its one electron. So I place my electron there, and also another hydrogen would overlap head to head in this direction. So this is hydrogen, and then this is hydrogen with its one electron, which will be pointing downwards. But then have we satisfied everything there? Obviously not. We still have electrons that are not yet paired. So what happens here? We have side-by-side overlap that would occur. So let's say this would bond with this side by side. So this is a pi bond occurring there. Let me take this electron down. Okay, so this other electron that is not yet paired, we overlap side by side with this second electron over here, giving us another pi bond in here. So it means between the two carbons, we are having 2 pi bonds and 1 sigma bond from this head-to-head overlap. So giving us triple bonds in there. So if you want to draw ethyne in organic chemistry, that's why we draw ethyne as C. You have 3 bonds. So you now understand where that 3 bond is coming from. One of those bonds represents a pi bond, and then this is. So this is a pi bond, this is a pi bond, and then this is a sigma bond. And then you have your hydrogen. and then hydrogen. Remember, every single bond is a sigma bond. So this is a sigma bond. So the bond angle over here is actually what? We've already said it. It's 180 degrees. Take note of that. So this is basically what happens. What is the geometry? Like I said, the geometry is linear. So the geometry of ethine is actually a linear, a straight structure. So this is what happens in what? In sp hybridization of carbon. Now let's summarize the whole of this video. We've stated that what? Hybridization is the mixing of atomic orbitals. We discussed three types of what? Hybridization. sp3 hybridization, sp2 hybridization, and sp hybridization. For sp3 hybridization, we said that it leads to the production of what? 4 sigma bonds, 4 single bond, and we use methane in explaining that. We also explained what? sp2 hybridization using ethene as an example, where we said in sp2 hybridization, we have 1 pi bond, and then we have 1 sigma bond between the 2 carbons in ethene. So the carbon atoms in ethene exhibit sp2 hybridization, while the carbon atoms in ethine, as you can see on the board, exhibit sp hybridization. I'm going to draw the curtain close today. At this point, if you know you found this video exciting and you learned from it, if you found it helpful, don't forget to click on the subscribe button and the like button. I'll see you in my next video. God bless you.